Hey guys, in this video we will be looking at the polar coordinate system, motion within a polar coordinate system, as well as real life examples. In a polar coordinate system, any points can be described using a position vector from the origin. A vector having both magnitude and direction is given by r and theta respectively, where theta is the angle swept anti-clockwise from the positive x-axis. Before I move on, here's just a quick recap of some notations I'll be using in my calculations. A letter with an arrow above it represents a unit vector, which only provides direction and has a magnitude of 1. Also, I will notate using the Newtonian dot notation for derivatives with respect to time, where 1 dot above a function represents the first derivative, 2 dots the second derivative, and so on. In these diagrams, you will see two pairs of unit vectors, Cartesian xy and the polar r theta. Unit vectors r and theta are orthogonal exactly as xy, only rotated through angle theta in the anticlockwise direction. To find the relationship between Cartesian and polar coordinates, we must perform vector decomposition, shown in the right-hand side triangles, where the unit vector r is equal to the cos theta component of x plus the sine theta component of y, and that unit vector theta is equal to the negative sine theta component of x plus the cos theta component of y. The two equations may be written in a more compact way using matrix notation, where you should notice that it represents the general rotation matrix for an angle theta radians, anti-clockwise about the origin. Therefore, confirming our initial idea that r and theta are essentially a rotation of x and y unit vectors by theta radians anti-clockwise. Looking at this diagram of a band standing on a spinning stage, we can instantly apply what we've just learned. First, let's consider our Cartesian system. When the stage starts spinning, for a specific point, both the x and y coordinates will change constantly. However, if we consider the polar coordinates, r will always remain the same, no matter what speed or what direction the stage spins. But how would we find the velocity of someone on that stage, such as the guitarist or the drummer? Well, firstly, let's recall the equations for unit vectors r and theta. Now let's consider that the position vector r is the magnitude in the direction of its unit vector. We then substitute this into d by dt of the position vector r, and by using the product rule, we can differentiate with respect to theta. Following this, we substitute the equation above, noted 1 and 2 for simplicity, to reach an expression for velocity, which is equal to r dot unit vector r plus r theta dot unit vector theta. But what does this mean? Well, this expression describes the velocity at any given position vector with magnitude r and direction theta. Now, try pausing the video to find the second derivative of the displacement, which represents the acceleration of the system. Assuming you've had a go at it yourselves, here is the derivation. By taking the second order derivative of the displacement and substituting our expression for velocity, we can use the product rule to differentiate, giving out 5 terms, as there is 2 terms being multiplied and 3 terms being multiplied. We have already found the derivative of the unit vector r in our first derivation, which was equal to theta dot unit vector theta. The derivative of the unit vector theta is found in a similar way by substituting in the second equation followed by the first equation, giving out theta dot times the negative of unit vector r. Therefore, once we have grouped our terms into r and theta components, our equation for the acceleration in polar coordinates is equal to r double dot minus r theta dot squared, or by the vector r, plus 2r dot theta dot plus r theta double dot, or by the unit vector theta. But what does this mean for our example? Well, r double dot describes how you see the guitarist accelerate from an initial reference frame. The second term describes how the drummer sees the guitarist accelerate. The third term represents the centripetal acceleration if you are observing from outside the rotating system, but represents the centrifugal acceleration from the drummer's reference frame. The fourth term represents the Coriolis acceleration, which arises when the drummer sees the guitarist moving in a direction other than the rotational direction. The fifth term, the azimuthal acceleration, only arises when the angular velocity omega is not constant. Enough about spinning bands, now let's consider that satellite question that you always see on physics papers. Different situation? Sure, but the expressions we've just derived are perfectly valid. However, Take another look at the expressions we derived, and can you spot anything we can do to simplify the expressions when we use them for satellite questions? Pause the video and think about the radius of the orbit, and is there any modifications we can make? Did you notice? The radius of an orbit is taken to be constant as it is perfectly circular. Therefore, r dot and r double dot is equal to 0. This is what's known in mechanics as circular motion. As the motion of the satellite is also uniform, the rate of change of theta, often denoted by omega, is constant, so double dot theta is equal to 0. This means that the only term left is minus r theta dot squared. If we substitute omega into the equation, we get the following result, which I'm sure you recognise as the equation for centripetal acceleration. I hope this video was useful in understanding motion in a polar coordinate system. Thank you for watching, and we'll see you next time.